Hi all, this is another video for Maths and Algorithms, this time covering the topic of functions. This week, the basic objectives we have are the definition of the function to ensure that you understand what the function is. Then to see a difference between function and relation, we will learn quite shortly that every function is a relation, but not every relation is a function, and we will see how that comes about. Representation of functions to the Cartesian plane. So your Cartesian plane is your usual x and y axis that you would be familiar with. So we are going to teach you how to plot functions on that plane. Then look for the solutions of equations involving logarithms and exponentials. So quite a big portion of this video and the lecture will cover logarithms and exponentials. Just to introduce you to them, maybe you haven't heard or used them before, and applications of functions to programming. So more on applications of course will come during the lecture. Here I'm focusing as always on the key skills you will need for the test. So first of all, let's start by defining a function. What is a function? In programming terms, a function is something that takes an input and returns an output. This is no different in mathematics. You have some sort of an input, a value, usually a number, that goes into some sort of processing and then comes out changed. So here we have the general view of a function. So you have input coming in, some sort of rule is applied to that input, and an output comes out. For example, we have function f, which doubles the input. So if x comes in, imagine this is some sort of magic happening there, then 2x comes out. We double whatever came in. Similarly, if we had another function called g, which is square the input comes in, whatever the value was, it gets squared, raised to the power of 2. So that if we put input 3 into that machinery, it doubles it, it returns 2 multiplied with 3, and that gives you 6. If 3 comes in this one, then square it means that you have to raise it to the power of 2, and that means it came out as 9. So even though the input was the same, because the function was different, the other output came out, of course. Usually in mathematics, the way we write functions is this. We write f of x, meaning this is a function of input x. Sometimes input is called argument of a function. So argument x is taken and then it returns something else, depends on the rule. So for this particular f, the rule was to double it, so f of x is equal to 2x. That's how I can write it mathematically. Similarly to the other example here for g, we can write g of x, okay, which has the very same meaning. It's a function g taking argument x and returns x squared. This is the basic notation that we are going to be using. F and G and H are the most popular letters to be used, but it doesn't matter. It could be A of x as well. It really does not matter as long as the notation is the same. And then if we want to denote this process mathematically, we would say that function of 3, okay, my input is 3, is equal to 2 multiplied with 3, and that is indeed 6, as we said, and g of 3 is equal to 3 squared, and that's a 9, as previously stated. We did define relations last week, and we said that relation is a set of ordered pairs. So here we have a relation including 5 ordered pairs. 5 is related with 4, 7 with 3, 8 related to 3, 4 is linked with 2, and 7 is related to 2. Okay, for a relation, what we said is that we had an arrow diagram, for example, with the domain of R being written in there, and in the domain we had all first elements of every pair. So in that case we had 5, 7, 8, 4, and then 7. We don't need to put it for the second time because we don't want to repeat elements, as you would have recalled from last week. And then in that same arrow diagram, you would have the set of all second elements, which is 4, 3, and 2. And this would be called range of R. Okay, all the second elements of every pair is range of R. Okay, now we would draw arrows if the elements were linked. So 5 was linked with 4, 7 was linked with 3, 8 with 3, then 4 with 2, and then 7 with 2 as well, in that way. So here what you would notice is that 7 is linked or related with 3 and 2 at the same time. That means it is not a function, because for a function you need, for one input you have exactly one output. This is a golden rule of a function, if you like to call it that way. Okay, for every input you have exactly one output. So if our original set containing ordered pairs did not have that last pair, this 7 and 2, and it would finish here, my domain of R would still contain 5, 4, 7, and 8, and my range of R would contain 4, 3, and 2, with 5 being linked with 4, 7 with 3, 8 with 3 as well, and 4 with 2. You would notice that we have precisely this condition satisfied, that for every input I have one output. So this in fact would make R a function. I don't know what is the general rule, but I know that rule exists. I could write it as R of x is equal to y, where x belongs to domain of R and y belongs to range of R, in that format. Okay, so we had these symbols, of course, and the notation learned last week. So please double check if something is unclear in this video here or later on. So just to reiterate one last time, every function is a relation, but not every relation is a function. Similarly to what we had last week, every rational number is real, but not every real is rational. Okay, so keep coming back to those concepts. For functions, why they are nice, okay, is because once we have that condition that for one input you have one output, once you provide an input to your function, you know what to expect. You know that one single figure will come out, and then you can test against it, see if it really came out, if that was the output you wanted or expected to achieve from it. What we do with functions, though, in long term, is to look at how it behaves. What is the behavior of a function if we start manipulating inputs? If we start, let's say, increasing the input, or decreasing, or going to a specific value. That's important, especially in the fields of AI, but also has applications in other fields related with computer science. One of them is the efficiency of algorithms. So here I have a screenshot of a few functions plotted, a few functions which are quite common in describing the performance of an algorithm. So we have a red line there which is corresponding to y is equal to x squared. So this is your usual quadratic. It's a U shape which blows up quite quickly. As you can see, it keeps increasing quite rapidly even if x, the input, is low. Let me just mark this as well. X is the value on the horizontal axis. This is your input, the argument to the function, and then whatever comes out is a function of x. Okay, sometimes called y, but here we are going to talk about functions of x, so that's my notation there. So that if I ask you from the graph what happens if x is equal to 2, we see that this space is 10, so we are moving into 2 units per block. What happens with the quadratic? Actually, it's 4. So you can read off the values and you can see for yourself that for one input I will have only one output. If you keep stretching, you will never hit that curve again. So this is my quadratic. We have also the linear function, which just goes straight like that, which is y equals to x simply put, and then y is equal to logarithm of x, which is the nice green curve that doesn't increase that quickly, and finally you have y is equal to x log x, which is the orange one, which you can see that starts off slower than the linear, but actually it outperforms it at that time. What I mean by outperforming, and what did I mean before when I said that we are looking at the behavior of functions, is that then we can study, once we have the graphs, we can study what happens if x becomes very, very large. So you can see for x equal 30, for example, if you try to find the output, okay, of that function in linear, that will be here. In logarithms, we would be somewhere there, let's say, and then quadratic, it would take huge amount of numbers until that curve actually extends into this position. Now, how does that actually apply? Well, what's so important about it? Well, imagine that x, your input, is the number of terms that you need to sort out, for example. So you have your list of numbers and you need to sort it out. So you have some numbers in a list, you want to sort it in ascending order. Well, if you have 30 of these items, and if your algorithm has the function describing its efficiency to be x log x, which is that orange one, it will take, I don't know, whatever time it's here, maybe 50, maybe 60, but it will be the time needed to sort 30 items. If, however, your algorithm was performing its operation in quadratic time, x squared, this quadratic, before it reaches that stage here, it would be huge, maybe even in 2000s, maybe even in 3000s, whatever it is, but it would take more time, significantly more time, to perform its action compared to x log x algorithm. And it's in terms of the linear function, it actually brings us the lowest value, which is that 30. So for 30 items, it would take 30 seconds. As you will probably discover that later on in the module or afterwards, it's pretty much impossible to get a linear time algorithm when it comes to sorting or searching. However, computer scientists have come close to a linear solution. More on that, of course, you will learn later on. Now, our objective here is to make sure you can plot the function and understand what happens with it if you increase or decrease the input. So let's have an example of actually drawing a function. So here, my f of x, the function taking input x, is 2 multiplied with x squared plus 4. So that function takes the input, squares it, multiplies it by 2, and adds 4. So here we have a quadratic function, meaning that the highest exponent of x is 2. Any quadratic function looks like this. It's a U shape if the coefficient of x squared is positive, as it is in here, or if the coefficient would be negative, it would be U, but upside down. Sometimes I might refer to those as parabola. So we have a parabola if the highest exponent of x in a function is 2. If it's 3, if we have a cubic, the shape would be something like this. If it's 4, then the shape would be like that, etc. So we have different shapes that we need to expect when we have functions. But what will change is the speed of the turn, the place of the turn, and the general angle that this u is made. And this is defined by the coefficients, by the constant in it by itself, and by the coefficient of x squared and coefficient of x if there is one. So how do I draw it? The best approach, I think, is just to draw yourself a table and then start plugging in any inputs whatsoever, whatever inputs you want, and then finding out what the output is. So my general recommendation is to check the lowest inputs possible. So what you could check is 0, you can check 1, -1, you can check 2, -2, maybe even 3 and -3 if you want. The general rule is that you should be checking at least 3 points in order to plot the curve, but I would really say 5 should be the best number of points to check, purely because you want to really capture the curve. You want to know exactly where it turns and how it looks. So 5 is recommended number. I will check those 7, I think, that I did in here. So f of x, if I plug in 0 here, if I'm looking for f of 0, 0 is plugged in into the place of x, so I have 2 multiplied with 0 squared plus 4, and that equals to 0 plus 4, and that's a 4. So my f of x when x is 0 is 4. When argument of a function is 0, the value of the function is 4. If I plug in 1 instead, I will have 2 multiplied with 1 squared plus 4, and that equals to 2 plus 4, which is 6. So I have 6 in there. If I plug in -1, I will also have 6, because negative times negative is positive. So -1 squared will be still 1. 1 times 2 is 2, plus 4, that's a 6. If I plug in 2, I will have 2 squared, which is 4, times 2, 8, plus 4, 12. Similarly for the negative, for 3, 3 squared is 9, times 2, 18, plus 4, 22, and then similarly here 22. Now this is very symmetrical only because I have no coefficient of x. If on the top of that I had, for example, 3x or another term in x, then I might not have this symmetry. So this is purely based on my example, so keep that in mind. Don't just assume that for any negative input the output will be the same as it is for the positive input. That's not necessarily correct. So always check what your output would be. So here we have a Cartesian plane. Let's just mark this as f of x. As we know, this is on the vertical as always, and then arguments of the function x go on to the horizontal. So if my x is 0, so if on that line I'm at 0 right there, then the f of x must have a value of 4, which I believe is here. So I mark it up with a cross or with just a dot, doesn't matter, but I'm here at 0 and 4. So 0 and 4, just in case you didn't make that connection yet, it is my first ordered pair of that function. Okay, now 1, 6 is the next one, so my point 1, 6 needs to be plotted. So 1 is the value of x, so on the x-axis, as I call them, x-axis 1 has a value here, and then on f of x I need to have a value 6. So when 1 and 6 meet up, which is here, I need to draw a cross. Similarly, -1 and 6, here it's -1 on the x-axis, and that's a 6, so I mark it up. I also have 2 with 12, so when x is 2, I am going to go up to 12, which is there. So these two coordinates bring me here, okay, and then we have -2 with 12, so -2 and 12 go in there. And you would notice already that I'm not really able to plot 3 and 22 and -3 with 22, just because the actual scale, the zoom on that coordinates and also on the axis is too big. Nonetheless, we have the general shape. We know that we expect the parabola, and we know that it will turn here, being symmetric around the f of x axis. the y-axis. So we just extend it, and that's my function. From that graph I can then read off what would be the output for a given input. So now I can check, okay, so what happens if my input would be, for example, a half. If I'm at half, then my output is probably right like 4.5 of that function. Okay, but that's one of the things that you need to learn, and it's nice. It's nice in a way that I can easily test you on it. So this is a nice test question right there. Plot a function. So make sure you practice that. To practice it, I recommend you using the Desmos graphic calculator, which is available on App Store and on Google Play as a standalone application that you can download for free. You can also follow the link. If you are particularly lazy, you might want to go to the lecture slides, the PDF version of the lecture slides, which I provide on Moodle, and then just click on the link, or you can copy, or you can just Google Desmos calculator. Either way, that's what you will find out once you go to the application or to the web application there. Here what you can do, you can plot any function you like, and my recommendation is that you first of all come up with a function. Usually try to come up with few quadratics. Okay, that's my hint for the test. But anyway, try to plot few functions using pen and paper, and then go to Desmos and try to confirm that you have been correct, that you got the right shape of the function. So come up with a function. Function should have some sort of coefficient of x squared, some coefficient of x, and a standalone number. So take your pick. It could be anything whatsoever. For example, this could be a quadratic, and that is equal to y or f of x. You can type it in both ways, both formats. Try to look for input-output pairs like I did on this slide. Plot your function on the Cartesian plane, and then use Desmos to confirm whether you have been right or wrong. This way you can come up with countless examples, and you can keep practicing until you 100% confident that you will get your shape right on the test. Just because every function is a relation, it makes sense to talk about the domain and range of a function. And this is another way to look at the behavior of function long term. Rather than plotting it, we can algebraically evaluate what happens to it. So here, as an example, we have f of x, which is 3x minus 1. So we are tripling our input and taking 1 away from it. And this is restricted on a domain -2 up to 5, up to and including the endpoints -2 and 5. So x cannot take any values lower than -2 or higher than 5. Okay, it takes all the other values in that region. So what we might be interested in is to see what our outputs can be. What can we expect the function to do for us? So if my -2 is the input to the function, I take f of x, f of -2 rather, from there, plug it in, I will have -6 overall, -1, that's -7, and if I take f of 5, so the other endpoint, then I will have 3 multiplied with 5, 15, -1, that's 14. So I can say that actually my function of x is bounded as well. So the values of f of x will be between -7, including -7, and also up to and including 14. This is because of two reasons. First of all, because these are the values at the endpoints, so I'm confident these values are possible outputs of the function, of course, but also because of what the function is. It is not quadratic, it is not cubic, it is purely linear function, and any linear function is a straight line when you plot it. I know that the behavior of that function is a straight line, whether it's that way or that way. Okay, it will be one of those two cases. It is this one if the coefficient of x is positive, and it's the other one if the coefficient of x is negative. Of course, the angles, the starting points can differ, but that doesn't matter. The general idea is that in this increasing line, increasing linear function which I have in there, I will start with input minus 2 somewhere, which will be the lowest value of f of x if you imagine the Cartesian plane right now, and then at x being 5, it will be the highest possible value of f of x due to the nature of the curve. But anyway, that's what I can say. So my range of f is this when the domain of my function is that. Okay, let's have another example with a quadratic function this time. As we said before, we expect a parabola, and we expect parabola in this direction because the coefficient of x squared is positive. Now, what do I do here? I have domain going from 0 and including 0 up to infinity. What we are looking at here could be defined as actually, I don't think I brought it in last week, but R plus, so positive real numbers. And in case you are curious about it, R plus is the set of all x real numbers, of course, such that x is equal to modulo of x. So you see, only positive numbers satisfy this equality. So that's what R plus is. But actually, let me just refine it, because 0 is included. Actually, x belongs to R plus union with set containing 0. Okay, just to be precise of what we are talking about there. Nonetheless, that's my domain. Okay, that's my domain, that's where x will come from. Now the question is, what is the range of this function? Well, if we plug in 0 to this, f of 0 is actually 0 times 0 times 2, that's a 0, plus 6, it's a 6. And if you plug in a very large number to it, which infinity is in one way representing, then this will be huge. So actually, if you are a little bit naughty with notation and say that you are plugging in infinity, which is not a number in itself, you can actually say that it is infinity, it is big. But does it mean that my range is between 6 and infinity? That's a big question. Yes and no, not necessarily. It all depends on how this curve behaves, where it actually starts. Are we starting here on the curve, or are we starting here, depending where it is on the Cartesian plane? Let's just plug in 1, see what happens. If you plug in 1 and take f of 1 this time, then we have 1 squared times 2, that's 2, plus 6, that's an 8. If you plug in 2, then that means you have 2 squared times 2, which is 8 plus 6, 14. So you see that numbers are indeed increasing. But what happens if you plug in, for example, half? Okay, what's going to happen there? Half squared is 0.25 multiplied with 2, that's half, plus 6, that's 6.5. So it's increasing already. And that proves that at f of 0 we have the lowest value of f of x achievable. So that means we indeed start with 6 and finish at a very, very large number. Okay, so that's just an example of what we can do to analyze the performance of a function, the behavior of it in long term. With more examples during lectures and seminars, hopefully this concept will be clearer and you will be confident yourself to search for range if you have a given domain. Coming into the main part of the topic and of the video, we are going to talk about exponential functions and logarithms. So this type of function is a specific case of a function which we didn't really talk about before. A function which is exponential can be written as some number, some base, risen to the power of the argument. So the argument is a power, it's not the other way around like we had previously. So see, previously we had a fixed power that our argument was raised into. This time we have a number raised to the argument. Exponential functions are quite common and they are applied across the multitude of different areas and topics, etc. So they have applications in economics, in accounting, in biology, computer science, of course, in engineering. They are everywhere, really. As soon as there is a growth which is proportional to the size of the value at a given point of time, then the exponential functions are used to describe it. Now, in exponential functions, the base could be any number, so I can have function of x which has a base 2 raised to the power of x with, like I said, base 2, but it is quite curious that actually growth, which is a natural growth, is being described by this particular constant e. So you end up with function x equal to e of x being the actual exponential function known today. So that base is always 2.71 blah 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 blah. This is usually rounded to 3 decimal places like this, just simplified to 2.718. E itself is irrational number, so E is a member of real but not rational numbers. So just like pi, it never terminates. The decimal expansion keeps going on, and there is no pattern, so you cannot actually write it as p over q, where p and q are integers. So this does not actually satisfy the condition of rational numbers, as you would have known from last week. Nonetheless, the actual graph of exponential function is something we had before. Remember on that slide when I had 4 different functions describing algorithm performance, one of them was y is equal to e of x, which is the same as this one, f of x is equal to e of x. So you see, this sort of behavior that we want to discuss really and understand what's happening there. So we have f of x as always on the vertical axis and x on the horizontal axis as we had before, with 0 being there. Now what we are going to talk about in terms of the behavior, we are going to introduce limits very gently and see what happens if we approach a specific value. So you see, x itself, okay, because this curve expands and keeps going on both directions, we can see that actually the domain of x is between infinity and negative infinity. We can take any number, plug it in, and it will give me a value of that function. So that is possible. The overall domain is between minus infinity and infinity. But what is the range? What sort of values can my function take for when x is very, very big and positive, or what happens if it's very, very, very big and negative? So what we have in there is limit, okay, this is the notation, again, a new notation which I'm introducing right now, limit of when x is going to infinity first. If it approaches infinity, meaning when it gets bigger and bigger, based on the curve and also based on calculations, you can just start plugging in very, very large numbers into that function. What you will realize is that e of x actually, as limit of x goes to infinity, when it keeps growing, is actually infinity. In other words, using different notation, you can say when x goes to infinity, then f of x, which is e of x, goes to infinity. Okay, that's my claim. That's what we can say about the basic behavior of it. Also, what happens if limit x goes to negative infinity of e of x? Well, some of you might already guess. If you look closely, you will see that the value of the function actually keeps decreasing. It gets closer and closer to 0, but it will never cross 0. That's the property of exponential, that it will always give you a positive output. It will never give you a negative output or output of 0. Nonetheless, we say that limit as x goes to negative infinity of e of x is 0. It approaches as limit goes to negative infinity. But of course, this is just a concept. Infinity is not a number, so it will never actually equal to 0. It just gets closer and closer to it. And using this notation, of course, as x goes to negative infinity, function of x also goes to 0. Well, it goes to 0, as we said before. So exponential functions, I would suggest you actually go out and see for yourself how important exponential functions are. Like I say, they can be applied in finance, in economy, so compound interest could be described like this. In computer science, so for example, the processing power of computers, that's using exponential function. Also algorithms can be described by exponential functions. The bacteria growth on that trash that you forgot to throw out a week ago, that keeps growing as well exponentially, and so on. So many different things in nature that use exponential functions. And if you cast your mind back to the induction, we had the secretary problem. If you're not quite sure what I'm talking about, have a look at the induction materials in Moodle. But we had the secretary problem, which included a solution which is called 37% rule. So you are searching for the best secretary for 37% of your time. You're just looking and establishing a standard, and then you're picking the best secretary who comes after that. So it's called look and leap procedure. But the solution was 37%, which at the same time in class I mentioned that this is equal to 1 over e. So again, that number e came out as a solution to such an interesting and difficult problem that took mathematicians about 10 years to solve. So revisit that from induction activities if you're interested in that sort of things. Now, laws of indices. So we have 3 laws of indices which you need to know coming into the test. You will be tested from it. No formula or any hint will be given in the test. You need to remember those. So here it's basically talking about how you're dealing with mathematical operations which use indices. First rule or first law of indices is how you're actually dealing with multiplication of the same of numbers to the same base. So let me give you an example. So I will be giving these laws as examples really. If we have a particular exponent, let's say with exponential number as its base, so let's have e to the power of 2, and we want to multiply it with exponent to another power, as long as the base is the same, we can combine the powers in the following way. We can just add up the powers, and that results in e to the 5. So that means by the first law of indices, if you have multiplication of exponents raised to different powers but of the same base, then you're adding up the indices. So a short illustration with base 2 might actually convince you that this is really the case. If you have 2 to the power of 3 multiplied with 2 to the power of 2, that's supposed to be, using this law, 2 to the power of 3 plus 2, so I can note that down, and that equals to 2 to the power of 5. So let's double check that. Powers of 2 are 2 times 2 times 2, 8 times 2, 16, and again times 2, 32, 64, 1, 2, 8, etc. So we know that. But anyway, 2 to the power of 3 is 8. So we would have 8 in here multiplied with 2 to the power of 2, which is 4. That's supposed to give me 32. And if you look closely at the powers of 2, fifth power is indeed 32, so the equation holds. And you can check that with any base and any indices. and it will come true. So algebraically, I can write this one as e to the power of x multiplied with e to the power of y is equal to e to the power x plus y. Okay, so that's your first law of indices that I need you to remember. Okay, so coming into the second rule. Second rule is quotient rule. So e to the power of 5, for example, divided by e to the power of 2, let's say, is e to the power of 5 minus 2, and that is equal to e to the power of 3. So quotient of exponentials using the same base is equivalent to exponent, the same base, to the power of the difference of indices. So you take the difference if you had quotient of numbers using the same base. So that's e to the 3. Again, use it with a simplistic example when base is 2. So 2 to the power of 7 divided by 2 to the power of 4. Let's say that's supposed to be 2 to the power of 7 minus 4, and that's supposed to be 2 to the power of 3. Let's double check it. So 2 to the power of 7, if you go to the seventh one, that's 1 to 8. So you would have 1 to 8 in the numerator of the fraction, divided by 2 to the power of 4, which is 16. And that certainly gives you 8 if you calculate it. And then if you look at the 2 to the power of 3, we already know this is 8, so it works. Test it with other bases, other exponentials, it will still provide you the same answer. The third and final law of indices is the law of raising to the power. So if you have a particular exponent raised to the power of 4, let's say, and all of this is raised to the power of 2, then what you should be doing is actually multiplying the indices, and that means you have e to the power of 8 overall. As before, let's test it with base 2. 2 to the power of 4, let's say, raised to the power of 2. As we have, similar to this one, we have e to the power of, 2 to the power of 8 overall. And 2 to the power of 8, we have 7 terms in here, so the next one will be 256. So we have this to be 256. If you did that first, 2 to the power of 4, that's 16, so you would have 16 to the power of 2, and you can check that one using calculator, and indeed it is 256, so it works that way. And just to give you algebraic versions of these laws, so the laws that actually come up in literature, and the format you should be remembering these laws is that if you have e to the x divided by e to the y, the power of y, then that means e to the power of x minus y. So you take the difference of indices if you had a quotient of terms. Of course, you add up the indices if you had the product of terms. And the third law states that if you have e to the power of x all to the power of y, then this is equal to e to the power of x multiplied with y. So these are the three laws you need to remember. That you will be tested on it for sure. So let's have some examples just to finish off the laws of indices, just to make sure you remember them. So feel free to pause the videos before I reveal the solutions and double check if you got them correct. Here I have 3 to the power of 2 multiplied with 3 to the power of 3. So that will be 3 to the power of 2 plus 3. Okay, multiplication of terms means that you need to add up the exponents. That's the first law of indices. So this is 3 to the power of 5, and overall 3 to the power of 5, I believe it to be 2, 4, 3, which can be easily verified if you have multiplication of 3 going on at the side. So 3 times 3 is 9, times 3 27, times 3 81, and times 3 is 243. We have multiplication of 3 5 times, so this is indeed true. Now, you might be asking yourself, okay, wouldn't it be easier to just square 3 to get 9 and cube 3 to get 26? 7 and just multiply 9 with 27? The answer is yes. Of course it would be easier for a human being, but when it comes to computational powers and the computational time, you always want to reduce your operations so that it becomes faster. It can be operated in a quicker time. So actually raising to the power only once, like we do here, to the power of 5, is less resource consuming and time consuming than actually taking two exponents and then multiplying them by itself. So it's just about saving time from a machine perspective. Anyway, let's just look at this example. So we use second law of indices there, which states that we need to take away the exponents or the indices. So if we have the quotient, what we do is we combine it in this format. So we have the first index minus the other index, which is 2x, and overall, if you remember from algebra, we have to reduce this coefficient because these are like terms, so this is equal to e to the 4x. Okay, and basically we can't do anything with it at this stage because we don't know the value of x, so we just leave it in this format. And then third law of indices, let's test it there. So remember, if you have an exponent, so already an exponential number raised to another power, then you multiply the powers together. So you keep the base, and then 2 multiplied with 3, let's just denote it here, or 3x, 2 multiplied with 3x, and this is equal to e to the power of 6x. Nothing more than that, and this is again the final solution you can give because you don't know the value of x. X could be any value again at this stage. So let's just have one over the top example, so combining more than one of these rules. So we have e to the power of 3 multiplied with bracket e to x minus 3 all squared over e to the power of 2. Rules of BIDMAS still need to be applied, so we need to deal with bracket, and the only problem is that with the things inside of the bracket we can't really do anything. So the next thing to do is actually to evaluate this exponent. So let's just rewrite this in a different format. We have e to the power of 3 multiplied with e to the power of 2x minus 3 multiplied with a bracket again e to the power of 2x minus 3. So what I'm saying there is that since I'm squaring the bracket, I'm just multiplying bracket with a bracket. So let's just expand it, just like we expanded quadratics. Thus we will need to multiply everything from the first bracket with everything else in the second bracket. So leaving e to the power of 3 on its own for now, when we expand the brackets we have e to the power of 2x multiplied with itself. So you will have e to the power of 2x all to the power of 2, then minus 3 multiplied with e to the power of 2x gives you minus 3e to the power of 2x. Then the other minus 3 multiplies with e to the 2x, give you another minus 3e to the 2x, and then minus 3 times minus 3 gives you plus 9. All of this is of course still divided by e to the power of 2 that we have in there. Let me just use this space on the slide to continue. So we will have equal, okay, what is there is e to the power of 3, and in the bracket you will have e to the power of 4x, because I apply the third rule of indices there, multiplying indices together. Then I collected like terms, so I ended up with minus 6e to the 2x, so that's a minus there, and then plus 9 over e to 2x, bring e to the 3 and multiply it with every term inside of the bracket. So what you will have, okay, you will have a multiplication of e3 with e to the power of 4x minus 6e to the 2x multiplied with e to the 3 and plus 9 multiplied with e to the 3. So this term e to the 3 multiplies everything inside of the bracket, and I'm just using the property of multiplication, which is its commutative or commutativity. of the product, so that doesn't matter if I write it before or after the term, hence the discrepancy in here. It's still valid, and of course all of it divided by e to the power of 2. So let's just see what happens. E to the power of 3, sorry, e to the power of 3 plus 4x is the first term, only because we're supposed to be adding indices together using the first rule, minus 6e to the power of 2x plus 3, and also plus 9e to the 3, and then all divided by e to the power of 2. And what the result will be, apologies for squeezing it in like this, but I'm kind of running out of space. What will happen now is that we need to bring this and divide every single term by e to the power of 2. So take 2 away from every index, in fact. So we will end up with e to the power of 3 plus 4x minus 2. 3 minus 2 gives me 1, so e to the 1 plus 4x is the first term, if I bring this quotient in, minus 6 e to the power of 2x plus 3, again minus 2, that is 2x plus 1, and also that last one will be plus 9 e to the 3 minus 2, so e to power 1, or just e. So that's what we could write it in the lowest possible terms. Of course I forgot e, so beg me pardon. It's all because of the space restraint. Nonetheless, have a look for yourself, try to do it on your own and see if you end up with this. What I try to achieve using this example is to show you how to kind of bring it down to the lowest possible format of the expression, which comes in handy especially when you're solving something or looking for a particular value and you want to save some time, or you want to make the program more efficient there. Next we have logarithmic functions, which are the opposite of exponents, and logarithms themselves provide a different way of understanding indices. Beforehand, using exponents, we could write statements like 10 to the power of 2 is equal to 100. Okay, this is equation, no x's, nothing to find, is just a pure equation there. That's something we could write. The same statement could be written in logarithmic form as logarithm to the base of 10, so the base number 10 of 100 is 2. So in other words, I need to bring 10 to power of 2 to make it 100. Okay, that's the way we are understanding logarithms. And general convention is that if we have log of 10, we just write it as log. So if the base is not mentioned, then you simply don't have to, you have to assume that the base is 10, nothing else. Of course, logarithms of different base are still possible. So if you had 2 to the power of 5 is 32, which we know from previous slide, and also if you use calculator that comes out, you could write it as logarithm to the base of 2 of 32 is 5. So in other words, we are looking for a power that if we raise our base to that power, we will get the argument of that function. I'm a little bit naughty there because I'm not using brackets. However, I do recommend that you use the brackets so that you can see the connection between the notation for a general function and the notation for the logarithm. But in literature and generally, you don't have to put the brackets. They are not mandatory, they are optional, but they help you see it more clearly. So the argument of the logarithm is inside of the brackets there. So logarithmic function, it has this shape. It's an inverse of the exponential function, and again it has multitude of different applications in many different fields of life. So again, I could repeat myself from the previous slide. In lecture, actually, I will provide you with a nice link that shows you how logarithmic functions click in during the machine learning process. So when you develop AI, loads of things that your machines are doing can be modeled and should be modeled using logarithmic functions, among other things. But logarithmic functions play a part in it. Okay, so what we have in there, again, we want to discover the behavior or talk about the behavior of the log function. So here we have log to the base of 10, okay, using that convention of x. So if x goes to positive infinity, so that means if it keeps growing and growing on the x-axis, remember, which is here, then what happens to f of x? Well, whether it's clear or not, actually it keeps increasing. It doesn't increase in a very fast manner, but it still keeps increasing to infinity. Okay, it's a better function in terms of growth than quadratic or than exponential function. So it grows much slower, but it still goes to infinity. What happens if x goes to negative infinity, however? What happens to f of x? If you look at the picture, it actually approaches minus infinity. Okay, it never touches the f of x axis, okay, but in terms of f of x, it actually keeps decreasing and increasing until negative infinity. So what we say about the logarithmic function is that limit as x goes to infinity of the log x function that is equal to infinity, and limit as x goes to negative infinity of logarithm of x, and that is equal to negative infinity there. So it keeps growing and growing into the negative a bit more. From the picture and from the fact that exponential curve never actually has negative outputs, here we cannot have negative inputs. Okay, so the domain is restricted for the logarithmic function, and the domain of the function, domain of f, if you like to write it this way, is actually now let me just bring in another notation so it's a bit easier, then I will confirm with what we already know. What we can say is the domain is 0 up to infinity there. So we use curly brackets to say that these points are not included. Sometimes you can see domain defined like this, for example, which would mean that we have x that can be equal to minus 2, but it's definitely bigger than minus 2, and lower but not including a 5. Okay, so curly bracket means that the endpoint is included, or a normal bracket rather, and then square bracket means that the point is included in the domain. Here infinity is not a value, so we need to use normal bracket, and 0 is not included because the value cannot ever be 0. Alright, so that's new notation if you like to think about it this way. Old notation would be to say, of course, that it's between 0 and infinity like this. This is my domain of x. To give the range of the function between minus infinity and infinity. Okay, so that's just the behavior of the logarithmic functions, and let's just explore the laws involved in logarithms. So again, you have few laws that you need to remember coming into the test, so you need to learn them off by heart. First law of logarithms, okay, that you need to remember is the addition of logarithms. So if you have log of, let's say, 5 and you want to add it to logarithm of 4, to combine it and to make the process more efficient, what you can do, you can take logarithm of the product of their arguments. So that means logarithm of 5 multiplied with 4 giving you 20. Okay, so addition of logarithms is equivalent to the product of the arguments. And that is really the opposite of the first law of indices. With law of indices, we have that if we raise a particular base to one power and then multiply with another number which is the same base multiplied with another power, so we have multiplication of exponents, we would add up the indices. Here, if you are adding up the logarithms, which, as you know, they return the value of the indices, is the same as multiplying the arguments themselves. So there is definitely a connection between laws of indices and laws of logarithms. They just operate the other way. Multiplication of exponentials results in adding up indices. Here, adding up logarithms ends up with product of the arguments. Second law of logarithms is that if we have a logarithm of, let's say, 60 there, and then we take away a logarithm of 12, for example, the actual difference of logarithms is the quotient of their arguments. So again, reverse of the exponential. So logarithm of 60 minus logarithm of 12 is logarithm of 60 divided by 12, so that's a 5. Okay, so that's the second law. And then the third law of logarithms, if you have a number in front of the logarithm, so two logarithms of, I don't know, 5, for example, that means you can bring this number inside of the argument by actually raising the argument to that power. So what we would have is we would have logarithm of 5 raised to the power of 2. That's how this 2 comes in here. If that number was 3, we would have 5 to the power of 3, etc. So that is equal to logarithm of 25. Okay, so these are the laws. If you want the algebraic versions of the laws, then of course you have logarithm to the base a. It's important to note, even though I didn't do that, is that the base has to be the same. I didn't do that, but then again I did, because I said logarithm of 10 is just log. We sort of forget the base if we are talking about logarithms of 10. So even though I didn't point it out, the base of the logarithm was always the same throughout my examples. Nonetheless, the generic algebraic law of logarithms, the first one is logarithm to the base of a of some number, so let's just call that number b, plus logarithm to the same base, so the bases have to be the same, of another number c, means that we take logarithm to the same base again of a multiplied with c. Add your brackets if you prefer to use them. Like I said, they are optional. Second law, logarithm to the base of a of another number, so b minus logarithm to the same base a of yet another number means that you take logarithm to the same base a of the quotient b divided by c. And the last one is that if you have a number multiplying your log to a particular base for another number, so number c, that means you have logarithm of your original argument to the power of the number outside of the logarithm. Okay, so these three laws you need to remember again going into the test, as you will be tested on them. You will have some examples where you need to apply them. So let's test our knowledge of the laws of logarithms and apply them to some examples. So first example will be a little bit odd. It will look odd at the first glance. It's because on purpose I have skipped one law of indices. I will give it to you now and then I will tell you why I skipped it. So basically we have another law of logarithms which states that if you have a logarithm to a particular base of some number, so let's call it b, then what you could do is you could take logarithm of some other base that you might be more familiar with, okay, so introducing a new base of the argument itself divided by logarithm to the same base c but of the first base. So you break down the first base and sort of map it to something else. Okay, transfer it to something else. Now, this law is important. You should know it. You should learn it. Hopefully, it will come handy sooner or later, but it's not going to be tested. It's not going to appear in your test, and hence why I don't think we should focus too much on it in this video. However, since this example is here, let me just solve it. You have noticed by now that I had a logarithm to the base of 100 of 1000. What I wanted to do with it is to bring it to log of 10, which is again written as just log, and use that rule to break it down, that operation in this way. So log of 10 of 1000, I'm asking myself what power I need to bring 10 into to get me 1000. The answer is 3. And then at the bottom again, what do I need to raise 10 into to get 100? The answer is 2. So overall this is 1.5. And just to verify, this really is the answer, because remember the question was what is the power of 100 that gives me 1000. If we had this 100 raised to the power of 1.5, using the first law of indices, going back to the previous set of laws, I can break it down into 100 to the power of 1 multiplied with 100 to the power of 0.5. Okay, because these power need to be added up, and therefore we end up where we started. 100 to the power of 1 is of course 100. If you remember what we did in the very first topic of the semester, 100 to the power of half means square root of 100, and that gives me 100. Of course, that was a multiply, beg me pardon, multiplied with 10, and that is indeed 1000. So we used the law. We didn't have to use calculator to actually find out the real answer. However, more often than not, you will find yourself in a situation where numbers are not very nice, so the calculator is your only option. There are ways to evaluate logarithms without them, just by hand, pen and paper, but they are quite difficult to follow, and they're quite long, so I'm not going to introduce them whatsoever, and I don't recommend you to use them at all. Now let's use the first law of logarithms here that we learned previously. So if you remember, addition of logarithms means you have to take product of their arguments. So we take log of 100, and technically you could leave it like this, or you can evaluate it. You know that the base is 10. What do I need to raise 10 into to get 100? Well, I need to raise it to the power of 2. So the result of the operation is 2. 10 to the power of 2 gives me 100. Next, logarithm of 5x squared minus log of 10x. The difference of logarithms is the logarithm of the quotient of the arguments. So here we take log of 5x squared all divided by 10x, and we should be simplifying this and leave it in the reduced format. So 5 and 10, they can be divided by 5 to leave you with 1 and 2, and also remember that x squared is x times x, so we can take the power here, take the x there, and end up with logarithm of x over 2, so half of x there. Okay, of course stop there because we don't know the value of x. We just leave it in the algebraic format, in the most simplified format we can. And finally 2ln 3x. Now ln is something I didn't mention at all, so let's just bring that concept in. So remember when I said that log to the base of 10 is just log, that by convention, by agreement, that's what we understand. If we don't state the base is 10. Similarly with ln, ln is the natural logarithm. Okay, so we call it natural logarithm, and this is when we take logarithm to the base of that special number e that we introduced earlier. So natural logarithm means the base is e. But the laws apply in exactly the same way. They apply to any base. So here what we can do, we can take logarithm the natural logarithm of 3x all raised to the power of 2. Okay, that number, if you want to bring it in, means you have to square, in this case, square the whole argument. The whole argument, which is 3x. So a number and a variable. So that means we have logarithm, the natural logarithm of 9x squared. 3 times 3 and then x times x. Okay, to leave you with this. To finish off the video, just a couple of very quick equations. Okay, we will expand more on this during the lecture, but here we have a couple of equations involving exponentials and implying the use of logarithms and how to solve them. So here I have 5 to the power of x equal to 3125. So the question here is, what power I need to raise 5 into to get 3125. So we can reverse this statement by using logarithms. We can say that actually the power x can be found by taking logarithm of 5, okay, base 5 of 3125. That's how you would basically write it down, and that's what you need to type in into your scientific calculator. Here is the reason why scientific calculators in this module are so important. Functions such as logarithms or exponents and many others that we will come to use in the next weeks, they are very handy in here. They are in the scientific calculator, so make sure you have one with you going into the test and exam. Now, we can just plug it in and use the calculator to do it. We could also try to see what happens if we start raising 5 to certain powers. So 5 to the power of 1 is 5, times 5, 25, times 5 is 125, times another 5 is 625, times another 5 is 3125. So whether you use calculator or not, actually 5 to the power of 5 is 3125. So x is equal to 5 in this case. And again, numbers are very nice just for illustration purposes, but more often than not you will need to use calculator to evaluate it, because the number doesn't necessarily have to be a whole number. The power itself could be anything, could be 4.2 for example, if that number on the right hand side was different. So make sure you are comfortable on using your calculator to calculate logarithms. If you're not sure how, please approach your tutor and then they will be happy to show you, no doubt. I will be happy to show you at any time after the lecture, no problem. 7 to the power of x plus 14 is 2387. Nothing much different. Remember, from our first topic, we want to get rid of plus 14 because it doesn't involve the variable I'm looking for. So transport it to the other side. You will find that 7 to the power of x is equal to 2401, and very much the same approach applies. So you find the x by taking logarithm to the base of 7, base of that exponent is 7, of the big number 2401, and again use your calculator or look for the expansion of 7. So 7 times 7, 49, times 7 is 343, okay, times another 7, that's 2401. So actually the power I'm looking for is 4. So we have 7 to the power of 4 giving me 2401, which is the solution to this equation. So again, during the lecture we will have few more, and we will have an example of using exponents to find a logarithmic the solution to logarithmic equation. So the other way around, in other words. Here we use logarithms to find the exponent. We can obviously use the opposite logic to find the other thing. So more on that in session itself. So I hope this video showed you a little bit of what we are going into, and more will be discussed in the lecture. Okay, so more motivation, especially the application of those functions, will be discussed there. Between now and the session itself, I would recommend that you do some reading so you are more prepared. Chapters 6 and 8 this time of Mathematics for Engineers will do the justice. So chapter 6 talks about functions in general and how we graph them, how we plot them. It gives you exercises on those. Chapter 8 is more about logarithms and exponentials themselves, so practicing on using those laws. Let's see how many laws you remember coming into the lecture. That will be very interesting to see if you watch the video. So thanks for watching. I will see you in the next one.